Good afternoon. I am Shailendra Singh Ojha, Assistant Professor in Department of Electronics and Communication Engineering. Today I am going to discuss feedback amplifiers. If I will talk about the term feedback, then one thing that comes into mind is something that is coming from output towards input. If I will, because generally signal flows from input to output, but in case of feedback, some part of output will come back to the input. So let us discuss this concept. What is the need of feedback amplifiers and what are the advantages of feedback amplifiers? So before discussing these, let us discuss the block diagram of feedback amplifier. Actually, if you consider this is the simple amplifier and some part, this is you are applying some input, output, and this output has been given to this feedback network actually. And output of feedback network will be somewhat less than x naught, and it is known as feedback output. And this is beta. Beta is nothing. Beta is the feedback factor which is equal to xf upon x naught, just like A is equal to x naught upon xi. So now this part or the output of feedback network will be given to this input where there is one already actual input signal xs and this is xf. So if this is plus and this is minus, if it is adding in a subtractive way, then it is called as negative feedback amplifier. If plus sign will be there, if it will be in the additive manner, then it will known as the positive feedback. So generally, negative feedback amplifiers are used for the purpose of amplification. Positive feedbacks are also useful, but they are useful when we will design the oscillator circuits. That means the circuits which has the capability, the circuits which have the capability to generate the various type of waveforms, especially sinusoidal waveform. We will discuss positive feedback in the later section. Here we are going to discuss negative feedback. And generally, negative feedbacks are used for the amplification purpose due to some advantages, like it desensitizes the gain. That means the value of signal gain is less sensitive to the variation in the value of circuit components, such as might be caused by the change in temperature as well as some other things. Next is the reduces the non-linear distortion. That means the output is proportional to input, or in other words, we can say that the gain becomes constant and it will be independent on the signal level. Next is reduces the effect of noise. It minimizes the noise. We will see how it can minimize the noise. It controls the input and output resistance. That means if you want that input impedance should be high, you can choose proper negative feedback topology. If you want that input impedance should be low, then you can choose another topology. Or simply I can say that whatever requirement you have for the input and output impedances, you can choose the appropriate topology to get the desired input and output impedance. Next advantage is extends the bandwidth of an amplifier. As you know, the gain and bandwidth product is constant. So in case of negative feedback amplifiers, gain decreases. That means bandwidth will increase. So, if I will talk about the negative feedback amplifiers, then it can be understood by this block diagram. There should be one signal source. Then there will be a comparator or mixer network. Generally, it is known by the name mixer network. And this is the basic amplifier which is having the forward gain of A, and this is the sampling network. Now, it is the output from the sampling network will be provided as an input to this feedback network, and the output of this feedback network will be applied to the mixer network, which will mix the input from which will mix the output from this signal source and output from feedback. That means if here we have Vs and this is Vf, then it will mix Vs and Vf. So, it can be easily understood that there are 4 types of topologies of feedback amplifiers. One is voltage series feedback, voltage shunt feedback, current series feedback, current shunt feedback, and we will discuss these one by one. So, before discussing these individually, let us see these together. So, if we will see here and before discussion of these, I would like to discuss few things like mixer network, and one was the sampling network. Sampling network means it will be towards output side like this, that this is the sampling network. Sampling of voltage is done in parallel like this. Means sampling of voltage is done in parallel. Here in this case also, and sampling of current, see, it is done in series. Now, if I will talk about mixing, that means mixer network, voltage, mixing of voltage is done in series. And mixing of current, see, this is current. Mixing of current is done in shunt. Parallel oblique shunt. So, if you will see this configuration, try to understand. Then at output side there is a voltage, at input side there is a voltage. So, it is actually voltage feedback amplifier. And earlier we have seen these 4 names like voltage series, voltage shunt, current series, current shunt. So, for example, if I will consider the name voltage series, that means it is the output side and it is the input side. For example, if I will consider its naming, then from output side there is a voltage and mixing is done in series. So, it is voltage series amplifier, voltage series amplifier. This is output side is voltage, input side towards input side, mixing is in shunt. So, its name will be voltage shunt feedback amplifier. If we will see here, output side is current. If you will see here, sampling of current is done in current and input is in series. So its name will be current series feedback amplifier. If I will talk about this, then here it is current and this shunt. So its name will be current shunt feedback amplifier. So this is the very easy way to remember these names and their diagrams. So now let us discuss these one by one. This is voltage series. This is the internal structure of the voltage amplifier. Voltage source has been connected here, ZL connected here. This is the feedback network, and beta is V0 upon beta is Vf upon V0. So Vf will be equal to beta V0. So in this way, this circuit can be drawn. So now let us analyze. If I will talk about here, then AF, that means gain with feedback, it is equal to V0 upon Vs. Okay. And what is Vs actually? If you will see here, Vi is equal to Vs minus Vf. Okay. So Vs will be what? Vs will be equal to Vi plus Vf. Okay. So you can write it as V0 upon Vi plus Vf. Now divide both numerator and denominator by Vi. Then you will get V0 upon Vi upon Vi upon Vi plus Vf upon Vi. It will be cancelled out, so it will be equal to 1 or not 1. V0 upon Vi is, sorry, it is A from this. So it will be A and it will be cancelled out, so it will be 1 plus. Now Vf upon V0 into V0 upon Vi. Can we write it like this? Yes, why not? Because V0 and V0 will be cancelled out. So Vf upon V0 is what? Beta, and V0 upon Vi is A. So you can see that it is equal to A upon 1 plus beta A, or A upon 1 plus A beta. This will be the gain with feedback, which is written over here. Now our next task is to find out the input and output impedance. We have already found out AF. Now let us find out input impedance with feedback. So II is equal to Vi upon Zi, and you know Vi is equal to Vs minus Vf upon Zi, and Vs is Vs, Vf is Vf upon V0 is equal to beta. So Vf is beta V0, and V0 upon Vi is equal to A. So V0 is equal to A into Vi. So it can be obtained like this. From this, II Zi will be equal to Vs minus beta I Vi. So Vs will be equal to II Zi plus beta A Vi. So it can be written as like this, because Vi is equal to II Zi. And you know, the input impedance with feedback is Vs upon II. So you can divide this whole factor by II. So you will obtain Zi plus beta A into Zi. That means Zi into 1 plus A beta. Now let us find out the output impedance. to find out the output impedance, what we need to do in this circuit, connect here dummy source and replace this Vs with the short circuit. So you can write the dummy voltage source. Due to that, whatever voltage will be appear will be equal to I Z0 plus AVI. And if Vs will be equal to 0, then Vi will be equal to minus Vf. So V will be equal to I Z0 minus AVF from this. And it will be equal to I Z0 minus A into beta V. So if you will take it towards this side, then you will get I Z0 is equal to V plus beta AV. So ZOF is equal to V upon I is equal to Z0 upon 1 plus A beta. So now few things can be remember over here, like one is the gain with feedback, that is AF. Another is input impedance with feedback, and it is represented as ZIF. And one more parameter is the output impedance with feedback, and it is represented as ZOF. If we will see here, 1 plus A beta term is there, 1 plus A beta term is there. In this case, it is multiplied, in this case, it is divided. So for all the 4 configurations, you can easily remember this, that the impedance with feedback will be either multiplied with 1 plus A beta term, or it will get divided by 1 plus A beta term. So let us see when it will be divided by 1 plus A beta and when it will get multiplied with 1 plus A beta. Here, see. In this case, output side is the shunt connection. That means output impedance will be divided by 1 plus A beta. Series side, input impedance will get multiplied with 1 plus A beta. In this second configuration, output impedance will be divided by 1 plus A beta. Input impedance will also be divided by 1 plus A beta. Why? Because both connections are shunt connections. In this case, that means current series amplifier, here output impedance will be ZOF will be Z0 into 1 plus A beta, because this is the series connection. And input side ZIF will also be equal to ZI into 1 plus A beta, because this is also the series connection. In this case, output impedance will get multiplied with 1 plus A beta, input impedance will get divided by 1 plus A beta. So in this way, you can analyze any amplifier, and this feedback gain or gain with feedback will be constant, and it will be equal to A upon 1 plus A beta in case of all the 4 feedback topologies. However, input and output impedance will get modified with the term 1 plus A beta. Either it will get multiplied or it will get divided by 1 plus A beta, depending on the series or shunt connections. And the method is very simple and same to as that of voltage series feedback amplifier for finding out the values of ZIF and ZOF for other feedback topologies. So you can easily find out this, and this is the table which will help you in remembering these relations. For voltage series ZIF, ZOF, means you can verify that series and shunt connection. So whatever we have talked about is clearly verified here, and you can remember only one concept, and these all 4 relations you need not to keep in mind, you can remember one thing, that if shunt connection will be there, the impedance will be divided by 1 plus A beta. If series connection will be there, then impedance will get multiplied by 1 plus A beta. So in this way, you can easily find out input and output impedance.